Have you ever stopped to think that even the most powerful and terrifying objects in the universe have an expiration date? Yes, we're talking about black holes. These cosmic creatures can swallow entire stars and distort the very fabric of space-time itself. For decades, we believed they were eternal. True gravitational monsters that only grew, sucking everything around them without ever giving anything back in return. But prepare to have your mind blown. Stephen Hawking discovered something revolutionary that forever changed our understanding of these cosmic giants. In the 1970s, he proved something groundbreaking. Black holes can die. And when I say die, I'm not talking about just any death. I'm talking about a fascinating process that connects the two most important theories in physics. Something that not even Einstein could have imagined. Hawking radiation reveals something incredible about these apparently indestructible objects. They can completely evaporate, transforming into pure energy over trillions of years. Like discovering that a great predator has a hidden weak spot. A vulnerability that we can only see when we unite quantum mechanics with general relativity. Today you're going to discover how this incredible evaporation process works, why smaller black holes die faster than the giants, and how this discovery might be the key to unifying all of physics. Prepare yourself for a fascinating journey from the quantum fluctuations of vacuum to the end of all black holes in the universe, billions of years in the future. When we think about black holes, our imagination takes us to a specific image. Something like a giant vacuum cleaner sucking up planets and stars like a whirlpool in space. This image is dramatic, but it doesn't capture the true nature of these fascinating objects. In reality, a black hole isn't exactly a physical object like a star or a planet. It's a region of space-time where something incredible happened. Gravity became so intense that it managed to completely curve the fabric of the universe. The difference between our popular perception and scientific reality is enormous. Black holes aren't voracious monsters that roam through space hunting their victims. They're more like extremely deep gravitational wells that only affect objects that get too close. Here's a surprising fact. If our sun were transformed into a black hole of the same mass, Earth would continue orbiting normally. It would just lose light and heat. What makes a black hole special isn't its ability to suck things from far away, but its absurdly high density concentrated in a tiny point called a singularity. The event horizon is a crucial concept for understanding how a black hole works. Imagine an invisible line in space that marks the point of no return. Anything that crosses this boundary is doomed to fall toward the center of the black hole, with no possibility of return. It's interesting to note that Einstein had difficulties accepting the existence of black holes, even though they were a natural consequence of his own theory of general relativity. But here we begin to encounter a fascinating paradox that has tormented scientists for generations. If nothing can escape from a black hole, not even light, how is it possible that they can die? How can something apparently eternal and indestructible simply evaporate and disappear? The answer to this question will take us on an incredible journey through the most advanced concepts in physics, revealing surprising connections between the microscopic quantum world and gravitational phenomena on a cosmic scale. Stephen Hawking was working quietly at his desk in the 1970s at the University of Cambridge when he made a discovery that turned physics upside down. He was investigating the properties of black holes using the tools of quantum mechanics when he noticed something completely unexpected. The calculations showed something incredible. These supposedly eternal objects actually emitted radiation, a very subtle form of energy. Imagine the surprise of scientists at the time. It was a bit like discovering something impossible. The greatest predators in the universe could also be prey to their own physical laws. Hawking radiation represents one of the most counterintuitive discoveries in modern physics. Hawking demonstrated through mathematics that black holes aren't the perpetual suckers we imagined, but bodies that continuously emit energy, similar to a very, very weak bonfire. This radiation is extraordinarily subtle and would be practically impossible to detect directly with our current technology. But the theoretical implications are absolutely revolutionary. It's like discovering that total silence is actually full of imperceptible whispers. The consequences of this discovery are breathtaking. If black holes emit radiation, this means they're constantly losing energy. And by Einstein's famous equation, we know that energy and mass are equivalent. Therefore, a black hole that emits Hawking radiation is literally losing mass over time, gradually shrinking like an ice cube melting under the sun. This insight completely changed our understanding of the ultimate fate of these cosmic objects. The most fascinating thing is how Hawking reached this conclusion purely through theoretical calculations, without any direct observational evidence. It was a feat of pure mathematical genius, similar to what Einstein did with general relativity decades before. The scientific community initially received this idea with skepticism. After all, how could something that doesn't allow even light to escape be emitting radiation? But the calculations were impeccable, and gradually Hawking radiation became a pillar of modern theoretical physics, paving the way for a completely new understanding of the nature of space, time, and gravity. To understand how black holes can die, we need to dive into physics' greatest conflict. On one side, we have Einstein's general relativity, an elegant theory that perfectly describes gravity on large scales, explaining everything from Earth's orbit to the expansion of the universe. On the other side, we have quantum mechanics, which governs the bizarre behavior of subatomic particles with impressive precision. The problem is that these two theories simply don't talk to each other. They're a bit like two completely different languages trying to describe the same reality. And right at the center of a black hole, there's a special place. The famous singularity, where these two descriptions of the world need to unite. The singularity is the point where our current physics simply breaks down. There, density becomes infinite, and the laws we know stop working, creating what physicists call theoretical incompleteness. It's like trying to use a city map to navigate the ocean. It simply doesn't work. To adequately describe what happens in the heart of a black hole, we would need a theory of quantum gravitation, something that physics' greatest geniuses are still trying to build. Hawking radiation emerged precisely from this attempt to apply quantum principles near the event horizon. The concept of quantum fluctuations is fundamental to understanding how the death of black holes happens. What we call vacuum isn't really empty, but a seething ocean of quantum activity where pairs of virtual particles appear and disappear continuously. These particles exist for incredibly short times, temporarily violating the principle of energy conservation through Heisenberg's uncertainty principle. It's as if the universe were constantly making energy loans that need to be paid back almost instantly. The mechanism of Hawking radiation works almost like a magic trick right at the edge of the event horizon. Close to this invisible frontier, something extraordinary happens with the quantum fluctuations of vacuum. When a pair of virtual particles emerges near the event horizon, the intense gravitational field of the black hole can separate them before they annihilate each other. The particle with negative energy falls irreversibly into the black hole, while its partner, now with positive energy, escapes to free space and transforms into real radiation. The most fascinating aspect is that the energy needed to make this particle real comes directly from the mass of the black hole itself. This creates a mechanism by which these cosmic giants can literally consume themselves. The relationship between the size of the black hole and the intensity of its radiation is surprisingly counterintuitive. Enormous black holes, with masses equivalent to millions of suns, emit incredibly weak Hawking radiation, with temperatures just a few fractions of a degree above absolute zero. On the other hand, minuscule black holes behave in the opposite way. Especially the primordial ones that theoretically formed right after the Big Bang would emit intensely powerful radiation, with temperatures of millions of degrees. It's an interesting contrast, the giants whisper, while the tiny ones scream with all their might. This inverse dependence between size and temperature creates a fascinating feedback loop. As a black hole loses mass through Hawking radiation, it becomes smaller and consequently hotter, accelerating its evaporation even more. The final moments of a black hole would be spectacular. It would become smaller and smaller, hotter and brighter, until finally exploding in a last burst of pure energy. Like watching a star burn its own existence from the inside out, transforming all its mass into quantum fields and photon emission that spreads through the cosmic void. In the current scenario of the universe, Hawking radiation is practically irrelevant to the fate of most black holes. These giants are constantly feeding, swallowing gas, stellar dust, and occasionally entire stars that get too close to their event horizon. The rate of matter accretion is impressive, millions of times greater than the tiny loss caused by Hawking radiation. So they continue growing constantly. It's like trying to empty a swimming pool with a teaspoon, while a garden hose continues filling it. The effect of evaporation is completely insignificant compared to the constant flow of cosmic material. But imagine a distant future, when all the stars have already burned their nuclear fuel and transformed into white dwarfs, neutron stars, or black holes. In this cold and dark universe, there will be no more free matter floating through space to feed these gravitational monsters. Without an external energy source, black holes will finally begin to feel the effects of Hawking radiation significantly. It will be a bit like turning off the hose and leaving only the teaspoon working, slowly but constantly emptying the pool. The black hole era will be the longest and loneliest period in the history of the universe. For approximately 10 to the power of 100 years, these objects will be practically the only inhabitants of a cold and empty cosmos. To put this in perspective, consider the current age of the universe, about 14 billion years. This time would be a blink of an eye compared to the eternity that black holes will spend evaporating alone in the void. During this astronomical time, they will gradually transform into pure radiation, returning to the universe all the energy they once captured. The evaporation process will follow a fascinating hierarchy based on the Schwarzschild radius of each black hole. The smallest will die first, shining intensely with extremely high black-body temperature during their final moments. The supermassive giants will have a different fate. Those that today reside at the center of galaxies will be the last survivors, evaporating so slowly that they'll take longer to disappear than the universe took to form its first stars. When the last black hole finally evaporates completely, the universe will enter its final phase, an infinite ocean of elementary particles and radiation spreading eternally through the immensity of space-time. Hawking radiation remains one of the most difficult phenomena to detect in modern physics, a brilliant theoretical prediction that still awaits direct experimental confirmation. The main challenge is that this radiation is extraordinarily weak compared to any other energy source around black holes. Imagine trying to hear a person's whisper while a symphony orchestra plays fortissimo beside you. That's the difficulty we face. The accretion disk around black holes shines intensely, with intensity millions of times greater than Hawking radiation, completely masking this subtle signal that we so want to detect. The world's most advanced telescopes are in constant action, including gamma-ray detectors like the Hess telescope, constantly scanning the sky searching for indirect signs of Hawking radiation. One of the most promising strategies is looking for sudden bursts of energy that could indicate the final evaporation of primordial black holes. If they exist, these small black holes would be right at the end of their lives, emitting intense radiation before disappearing completely in a final explosion of virtual particles and quantum fields. While we await direct detection, scientists around the world have created analog experiments that reproduce aspects of Hawking radiation in the laboratory. One of the most impressive uses is Bose-Einstein condensate, an exotic state of matter where atoms behave like a single giant quantum entity. By creating acoustic event horizons in this material, researchers can simulate conditions similar to those found near black holes, observing the emission of acoustic Hawking radiation that follows the same fundamental principles as the real version. These laboratory experiments do two important things. They validate Hawking's theoretical calculations, and they also open the way for a deeper understanding of quantum gravitation. It's fascinating to think that we can study some of the most extreme phenomena in the universe using equipment that fits on a laboratory table. Each successful experiment brings us a little closer to definitive confirmation that black holes really can die, transforming mass into pure energy through the quantum fluctuations of vacuum that permeate the entire cosmos, connecting the microscopic quantum world with the gravitational giants of general relativity. Hawking radiation represents much more than just a death mechanism for black holes. It's one of the few real bridges between two worlds of physics that seemed completely incompatible. For decades, general relativity and quantum mechanics existed as separate theories, each dominating its own territory without being able to communicate with the other. Hawking's discovery showed something revolutionary. It's possible to apply quantum principles in situations of extreme gravity, creating a hybrid territory where both theories need to work together, like discovering a common language between two cultures that could never understand each other. Although we still don't have a complete theory of quantum gravitation, Hawking radiation offers us valuable clues about how this unification might work. Each calculation related to black hole evaporation teaches us something new about the fundamental nature of space-time, virtual particles, and reality itself. It's a crucial piece of the cosmic puzzle that physicists have been assembling for generations, a clue left by the universe about its deepest secrets. The quantum fields that permeate the entire cosmos might be the key to understanding not just how black holes die, but how all of reality works at its most basic level. The impact of this discovery goes far beyond astrophysics, touching fundamental questions that not even Einstein could completely resolve. The singularity at the center of black holes represents a point where our current physics simply stops working. But Hawking radiation suggests that there's a deeper description waiting to be discovered. When we finally manage to unify quantum mechanics with general relativity, we'll be able to answer questions that humanity has been asking for millennia about the nature of time, space, and existence. There's genuine hope that our generation will witness revolutionary discoveries in this area. With advances in detection technology, we have increasingly sophisticated experiments with Bose-Einstein condensates and telescopes like HESS scanning the sky searching for evaporating primordial black holes. We're closer than ever to experimentally confirming Hawking radiation. Perhaps we'll be the first human generation to directly observe the death of a black hole, or even achieve complete unification of physics, finally answering the deepest questions about our universe and definitively connecting the worlds of the infinitely small with the infinitely large. Now I want you to reflect on something important. How does this new perspective on the mortality of black holes change your view of permanence and transformation? If even the most powerful objects in the cosmos can completely transform into pure energy, what other certainties in our lives deserve to be questioned? Hawking's discovery reminds us that the universe is in constant change, always finding surprising ways to transform matter into energy, density into radiation, complexity into simplicity. If you want to continue exploring the frontiers of physics, don't forget to subscribe to the channel and activate the notification bell. We have much more to discover together about quantum gravitation, singularities, quantum fluctuations of vacuum, and other phenomena that are shaping our understanding of reality. After all, we're living in the golden age of astrophysics, and each new discovery brings us a little closer to answering the deepest questions about our place in this extraordinary universe.